Hey guys, welcome back. Let's talk about race tables. So, there are a couple of things that we need to talk about before we start on the race tables. All right. One is the relationship between kinetics and equilibrium. So, your textbook is presented in a different order than we at TTC choose to present these topics. Here we talk about kinetics after equilibrium, and kinetics will be the second test. So, we're going to get to it, just not for a bit. But your textbook does state that there is no relationship between kinetics and equilibrium. All right. So equilibrium and kinetics are completely separate from each other. Now, I did mention that you will always reach equilibrium, but the kinetics may mean that happens slowly. Okay, that is very true. So there is that part of it. And kinetics again is the rate of a reaction. So it's how fast that happens. We'll talk about all the factors that go into that one for the second test. We're not going to worry about it now because that's not how we're doing this. And I want to make sure that I talk about that because we'll talk about it again, but it is in this chapter and I want to make sure you know. One of the other things that we need to be able to talk about is we talked about what does the equilibrium constant tell us in terms of do I have a lot of product or a little product when I'm at equilibrium, or am I roughly equal between the two? That's great. We can do that. But the other thing that we can do is we can use the equilibrium constant to calculate initial concentrations, equilibrium concentrations, the actual value of K. We can use the setup for that to use values at initial values and equilibrium values to actually calculate the K, which we've done previously. All right, we can do a lot of calculations with these things. But there's another factor that comes into this. And when we talk about that factor, it's called the reaction quotient. So the reaction quotient is actually listed as Q. And what Q is any conditions. The heck do I mean by that? Well, let's talk about what I don't mean by that. K is at equilibrium, only at equilibrium. Q, on the other hand, could be equilibrium, it could not be equilibrium. We have no idea. And that's why we're calculating Q, is to see, is it bigger than K, smaller than K, equal to K? So those are things that we want to do. We want to be able to compare Q to K. If Q is equal to K, we're at equilibrium. So the forward reaction is going to happen, the reverse reaction is going to happen in the exact same way it's always happened. We're not going to see any changes, so Q is equal to K. Awesome. What if Q is greater than K? Okay, so since it has the same form and products over reactants, and Q is bigger than K, that means I have more product, not enough reactant. So if that's true, then I need to go backwards. I have too much product, I need to break it down. I need to make more reactant, I need to go backwards. Okay, so that in that case, that reaction is going to have to break down the product as we've written it into reactants, and that's the direction that it's going to go. Okay, so it's going to shift backwards to make that work. Right? We also have Q less than K. And if Q is less than K, then I don't have enough product yet. So I need to make more of it. And that means I need to go forward. Now, we will talk about quantitatively or qualitatively how these things happen, how we can make these changes, and why the system will shift either direction. All right. But understand that this is what we're trying to do when we calculate Q, is to see what way do I have to go to get to equilibrium. Okay, this is a situation we have to work with, especially during chemical spills, because we may have something that we need to get rid of, and we need to know what its concentration is, and how can I manipulate that situation to get rid of it? What can I do to take care of it? There are a lot of things that we can do, but we have to think about not only what we think we should be doing, but everything else that might happen. Okay, that's why they pay people who do chemical cleanup a lot of money, because you have to think about a lot. Okay, so that's Q. That's our equilibrium, or actually reaction quotient. All right, so we can calculate a reaction quotient. Okay, questions, comments, problems on that? Hope not. Let's move on to our rice tables. Now, you've actually seen a race table before. I presented this table to you previously. I'm going to zoom into this so that we can see it again. We had H2 plus I2 going to 2HI. We had an initial set of conditions, and then we had an equilibrium set of conditions. And the equilibrium set of conditions came to us because we found out what the HI concentration was. And since we knew what that concentration was, we could figure out what the equilibrium concentrations of H2 and I2 would be because we knew what they were to start with. And so we could use those values to calculate the value of K. Okay, and that is what we are doing here. Now, the thing that I didn't talk about last time, we talked about the initial, we talked about the reaction, we talked about the equilibrium. We didn't talk about the change. So let's take a look at this change line that's right here. This change represents what physically happens when this reaction occurs. So if I want to make an HI molecule, I have to use an H2 and an I2 to do that. I have to take one of the H's from the H2 and one of the I's from the I2 to make an HI. Or I can take one H2 plus one I2 to give me two HIs, right? That's the stoichiometry of that reaction. So since I start with H2 and I2 and none of my product, the HI, then I know that every time this happens, every time I make an HI, it's because an H2 has been used and an I2 has been used. And that's where this negative X comes from. Because every time I make one of these, I have to get rid of one of these and rid of one of these. And every time I do that, I make two of these. Okay, so that's where those come from. Now, we can talk about the math that goes with this. So I know that this is 2x in the change, and I know what this value is that I was given. So I can set them equal to each other. I can say 2x is equal to 1.87 times 10 to the minus 3, and therefore x equals 9.35 times 10 to the minus 4th. So now that I have the x value, I can subtract that from the initial H2. So the 1.0 times 10 to the minus 3 minus the 9.34 times 10 to the minus 4th gives me 6.5 times 10 to the minus 5th. And I can take the 2.0 times 10 to the minus 3 minus the 9.35 times 10 to the minus 4th, and that gives me 1.065 times 10 to the minus 3. I can then take those values and plug them into my K expression to solve for K, which is 50.5. We've done that before, okay? So I know now how I can do that, and that's based on the stoichiometry of that reaction. So my stoichiometry has a direct bearing on what I put in that change row, okay? It is important that we do that. A couple of things that I need to make really, really clear. One side has to be negative, one side has to be positive. It is typical for us to write the reaction as we're intending to study it and make the reactants negative and the products positive. Is that always the case? No, it's not always the case. So, like I said, if Q is greater than K, then I have too much product and I need to go backwards, right? Then I'm going to be breaking down HI to make H2 and I2. So that would not make it, I mean, it's not logical to have it be negative X for H2 and I2 when we're making more of those. Can I do that? Can I leave it the way it is and not know which direction it's going to go? Absolutely, I can. Absolutely. There's nothing that says that that number, when it comes out to be negative, because it will, is nonsensical. Okay? It makes sense. But you have to understand what it means. What it means is that the way that you've written the reaction is not the way that it's actually working. And so rather than this being something you would subtract, it'd be something you had to add. So you'd subtract the negative number. Okay? Keep that straight. It is perfectly okay to leave it that way. However, some of us don't like it that way. So we may turn it around. And that's why I do a Q versus K calculation to see which direction it should go so I don't have to deal with that. Okay? So that's where that comes from. All right. I hope that that is clear to you. So we can calculate K using the values that we calculated using X. So we had X based on this concentration of HI, and we used that to calculate the equilibrium concentrations, which we then used to calculate K in exactly the way that we did previously. So it's exactly the same as what we did before. Awesome. Now, let us talk about equilibrium constants. So one of the ways that we do equilibrium constants is to calculate Kc. Okay, we can use these tables in exactly that way to calculate Kc. So I have these initial concentrations, I have my change just like I did before, I have my equilibrium expressions, so the values that need to be in there, those are then going to go into my table, and then I can solve for x. Now, what you see here is that this is pretty complicated math. It is very complicated math to do this the way that it's set up. And that can be problematic, okay? It takes a lot of time. It takes a lot of effort to successfully calculate these. I usually have to do them like 4 times. And that's a lot of work on a test. And using the quadratic is a big pain in the neck. So we don't necessarily do it this way, all right? Even though the setup is exactly right, we make some assumptions in doing this. And let me write down this rice table, since I haven't written it down yet. And then I'll show you what I did. Apologize. So I have H2 plus I2 goes to 2HI. 6.42 times 10 to the minus fifth is my initial concentrations. I took all of this data directly from this rice table. 3.37 times 10 to the minus fifth and 0 as my initial concentrations. My change is negative x plus 2x. That means my equilibrium expression is 6.42 times 10 to the minus fifth minus x, and 3.37 times 10 to the minus fifth for I2, and then 2x, okay? And that is what we have plugged in right here, all right? So that is what you see right there. Now, in order to do that math, we have to multiply these two together and then multiply that over there, and we end up with something that has an x2 and an x in it. So we have to use the quadratic equation to be able to do that. But do we always have to do this? And here's the thing. Here we do, because the value that we eventually find for x, I can see that the value for x is, where did I calculate it? Where's my value of x? Oh, so x equals, in this case, either 3.33 times 10 to the minus fifth or 7.49 times 10 to the minus fifth. Since x has to be less than what we started with, because we didn't have any product, the only answer that makes sense is 3.133 times 10 to the minus fifth. And that value is very, very close to what we started with. So in that case, we cannot make the assumption that I'm about to tell you about. But we often can assume that that x value is very, very small comparative to the initial concentrations. Okay, now it's not always, and if it's not, then we need to use the quadratic to solve this. But if we make the assumption, then we can do the math so that it doesn't look quite this messy. What do I mean by that? Well, if I take out those x's, if I ignore the x's, then my Kc is going to be equal to the 2x squared over 6.42 times 10 to the negative fifth times 3.37 times 10 to the negative fifth. So there are no more x's down in that value, right? And that's helpful because that means it's a lot simpler in terms of our calculations. And we know that this is equal to 50.5. So when we do this math, we can do 50.5 times 6.42 times 10 to the negative fifth times 3.27 times 10 to the negative fifth. And that's equal to, and I'm going to move it over here because I like having my x on my left-hand side. We're going to square the 2x. When we square that 2x, I end up with 4x squared because the 2 has to be squared as well. So that's my 4x squared. And so I can do this math. X squared is then going to be equal to the 50.5 times the 6.42 times 10 to the minus fifth times the 3.27 times 10 to the minus fifth over 4. And then I can take the square root of both sides to get x. And I can do that. That is absolutely something that I can do. When I do that, I find that my x value is 1.12 times 10 to the minus third. And that's really close to what I solved for previously. I mean, okay, it's not that close, but it's a value, and we can use that. Sorry, that's the, oh, excuse me. We can use that value to do this. So the math that you're going to be asked to do in this class will have you using that assumption that the x is small comparative to the initial concentrations, right? And therefore, we won't need to worry about it. Okay, so this is the kind of math that you'll be expected to do. Nothing heinous and complicated. We will never ask you to calculate using the quadratic equation. That is not something I think you need to do on a test. Okay? Let's talk about one more example for this. And we talk about the Haber process, of course, because I love the Haber process. N2 plus 3H2 goes to 2 NH3. Now this is a gas, this is a gas, this is a gas. And so they give me a Kp, and that's equal to 1.45 times 10 to the minus fifth at 500 degrees C. In equilibrium mixture of 3 gases at 500 degrees C, the partial pressure of H2, okay, so it's an equilibrium mixture. This is my R. I'm going to have an I, a C, a C, and an E. And I'm sorry you can't see the top of the table. There's only so many ways I can move this. I haven't been given any information about the initial conditions. It says that the partial pressure of H2, which is the second one, at equilibrium is 0.928, and that the partial pressure of N2 is 0.432. And they want to know what's the partial pressure of the NH3, okay? So that's what I'm looking for. This is all the information that I've been given. Okay, fine. Well, I have a value for Kp, so I want to look at what does that expression look like. It's Kp, so those are pressures. So the pressure of NH3, which has to be squared because of the 2 in front of it, over the pressure of N2 times the pressure of H2 cubed. Not squared, cubed. Because there's a 3 out in front. Okay, awesome. So I know that this is equal to 1.45 times 10 to the minus fifth. I also know that the N2 and the H2 have values. So the pressure squared for the NH3 is over the N2, which is 0.432, times the H2, 0.928, and that's cubed. So I can say that P squared NH3 is equal to 1.45 times 10 to the minus fifth times 0.432 times 0.928 cubed. So I've multiplied the bottom values. Oh, geez, I'm so sorry. You can't see that. So I've multiplied the bottom values, those two numbers that I plugged in there, the 0.432 that I plugged in for the N2 pressure and the 0.928 that I plugged in for the H2 pressure, which is cubed. I've multiplied those over times the Kp, which is 1.45 times 10 to the minus fifth. And that's equal to the pressure squared for NH3. So I have that P squared NH3 right here that I'm trying to solve for. So I can do the happy math that goes with those numbers that I've been given, 1.45 times 10 to the negative fifth times 0.432 times 0.928 cubed. And I end up with 5.01 times 10 to the minus 6. And again, all three of those have 3 sig figs. That's why I left it as 5.01, even though it came out as 5.006. That's why I wrote it up. Okay, now that is equal to the pressure squared of NH3. I want the pressure of NH3. So I can take the square root of both sides and get the pressure of NH3 is equal to that square root of that value. And that gives me 2.23 times 10 to the minus 3. And that's the pressure of NH3. Okay, so that's how we can find that value. Sorry, my 3 disappeared. That's how we can find that value that they're looking for. Okay, so when we're talking about Rice tables, a couple of the things I wanted to be able to talk to you about. I know that this is the setup for a Rice table. I write the reaction. I put stuff in the columns that they go with. I know what the change is. And of course I do. I know that the change here is negative x. This is negative 3x. This is plus 2x. I didn't need it right, in this table, but I know that that's true. I didn't need the initial concentrations to be able to solve for what I was looking for, because what I was looking for was based on the equilibrium concentrations. I know that the equilibrium concentrations of 0.432 and 0.928 are equilibrium values. So whatever I started with minus the 0.4 minus the x gives me 0.432. Okay, I know that whatever I started with minus 3x gives me 0.928. And I know that that 2x is equal to 2.2 times 10 to the minus 3. So if I needed to solve for x to calculate what the initial concentrations were, I could do that. Absolutely, I could. But that's not necessary right now. I use these tables and fill in as much as I can to see, what do I have? What have they asked me to solve for? And what else could I possibly need? Okay, if there's other information that I need to go figure out where I can get it from. But I didn't need anything else to be able to solve this. The Rice tables are not required. They are not a required part of problem solving unless it says, show me a Rice table or show me an ice table. If it says that, we need to see it. We want to see it. And you're not going to get full points if you don't show it. Okay? So it's important that you understand that these are not required. They are absolutely not necessary, but I find them extremely helpful to keep track of what information I have. Is it initial? Is it equilibrium? Where do I put it? Where does it go? And I don't think a lot about what it is I'm looking for until I make sure that everything is in the table where it's supposed to be. Okay? And hopefully that is a little bit helpful in terms of what we would use these for and how we would use them. Okay. Now, at this point, I'm going to say, do you have any questions? And I know you're going to go, I don't understand. I need to do more. Yes, you do. Yes, you absolutely need to do more practice. Is there more practice available? Oh, you bet. There's practice on ALEKS. There's practice in the in-class questions. There's practice in the practice problems that I've given you. There are some that are going to be at the end of this lecture that I'm going to put the answers on D2L for. You can ask me about any of them. The thing for me is, do you know how to solve for things that you would be asked to solve for? I've walked you through how to solve for a K. I've walked you through how to solve given some of the equilibrium conditions. I showed you some things where we could solve for equilibrium values, okay? So where we found what that x was and then used that x to figure out what the equilibrium values were for everything else, okay? So we can do that. Once we can find x, we can do that. If I have x, I can go back and calculate an initial concentration. So all the parts that you need have been shown to you. Have I shown you them in every permutation? No, I haven't. Okay, but that's what the practice is for. There will be lots of these calculations. Your comfort level with these tables is really important. Okay, we're going to be using them for all the acid stuff that we're going to do, for the solubility product stuff that we're going to talk about. This is going to be a big part of what we're doing this term. So practice, because watching me do it is not going to make you comfortable doing. Okay? Now, I'll get off my soapbox and stop preaching at you. I'm going to stop sharing, and I'm going to stop our recording, and I will talk to you soon.